So here's a problem like some of the ones in our book in the start of the exercises for 3.3. It's about the distribution of prime numbers. And here we're going to use, it's going to be a rare time when we use a result that's way beyond what we can prove with our methods, and that's the prime number theorem from the late 19th century, although it was first conjectured about almost 100 years before that. Um, so let's get into the problem. Like some of their problems, it's about area codes and phone numbers. It's pretty fun. So you live in Hackensack, New Jersey, and your area code is 201, smallest area code as far as I know. Your friend Bob lives in Owasso, Michigan, so his area code is the biggest one that I could find on Wikipedia, 989. You're each assigned a telephone number at random in your area code, and who is more likely to get a prime number for the whole 10-digit phone number? And how much more likely? Okay, so the first thing is for that first question, you don't need to know much about prime numbers, and it's really good if you can remember this. Without, even if you don't remember the details of the prime number theorem, that they get sparser as you go. Okay, so you are definitely more likely to get a prime number, and that's because primes are more. I don't know why that's a question mark. Because primes get more sparsely distributed as the numbers get bigger. But how much more likely? I guess that's why I had that question mark. Okay, is it drastic? Are you a lot more likely to get a prime number? Or is it a small difference? Okay, so that's where the prime number theorem really comes in. So the number of primes in the 201 area code, we do something a little bit weird because we have the prime number theorem. One of the simplest ways to make it fairly precise, a good approximation, is to look at the pi function, the cumulative counting function of the primes. Pi of some number is just the number of primes less than that number. So that's everything. For example, this is everything up through 202 and 7 zeros, but not including 202 and 7 zeros. So that gets all the primes we want, but a lot that we don't want, namely everything below that starts with something below 201. So we just subtract those guys off. Numerically speaking, this isn't a super great idea because we're going to be taking two rather huge numbers and subtracting them. So what we have to do is be really precise, get some good precision on these two numbers, but we can do that. Now, this approximately is really a big deal. This is not an exact count, but this is where the prime number theorem comes in, that pi of x is approximately x over the natural log of x. And so that's with 202 and 7 zeros, that's with 201 and 7 zeros. We evaluate those and we make sure that we keep a decent number of decimal places here so that we can start seeing decimal places, a good number of decimal places where it's significantly different. I would not want to take 9.4 times 10 to the 7th minus 9.4 times 10 to the 7th, which would be the result of rounding to two significant figures. You get 0. That's ridiculous. Okay, but I think I've got enough accuracy to get a pretty good approximation. And after all, it is just an approximation as soon as you use the prime number theorem anyway. Okay, so about 445,000 primes, roughly, in the 201 area code. And so the probability is just that divided by how many numbers there are, which is just 10 to the 7th. And you get about 4.45%. Let me show you an even quicker way. The book doesn't talk about this, I don't think. If you want a pretty decent approximation that isn't going to be very different, you can actually just say, you know, a slightly sloppier version of the prime number theorem is the probability that a number is prime if that number is near x is about 1 over ln x, 1 over the natural log of x. And if you just do that, I just went ahead and picked an x right in the middle of the 201 area code, 201, 5 and 6 zeros, and just take the reciprocal of the ln, you get about 4.667, about 4.7%. It's off by a little bit, but it gets you there. So this is, if I was just trying to do this very quickly and roughly, I would use this method. But it's nice to be a better approximation, which is the pi method gives you. Okay, so let's compare that to Bob. Okay, Bob, very similar calculation for the 989 area code. You take 990, that's the cap of the 989. 989 and 7 zeros, that's the floor. You compare the pi's. I took even more decimal places when I did the x over ln x calculations here because these numbers are getting bigger. Notice this is now in the 10 to the 8th. But I don't expect there to be more prime numbers, maybe even fewer prime numbers. And so I wanted to make sure I was getting a pretty decent accuracy here. So I actually took 7 sig figs here and subtracted. And you get about 415,600 prime numbers. Again, divide by 10 to the 7th, you get about 4.156%. Okay, and then compare that, remember, for the 4.45%. It's not that different. Because that natural log function doesn't grow very quickly, especially way out in the billions, when you increase from the 201 to the 990 level, it isn't actually increasing that ln by very much. And so it isn't decreasing the x over ln x by very much. If you want the quick and dirty way, it's the probability is about 1 over ln x, and I picked a number right in the middle of the area code, and you get about 4.345, about 4.3%. So again, those aren't super accurate, but again, the comparison is still pretty accurate. It's gone from 4, and about 0.5% down closer to about 4%. Not a drastic difference, but it's noticeable. Okay. If you want it even most quick and dirty, you'd say ln x is, it turns out if you use a little change of base formula, it's about 2.3 times the log of x, the log base 10, let me emphasize that, log base 10 of x, which is roughly 2.3 times the number of digits in x. So if you really want a quick rough and ready thing, just count the digits, multiply by 2.3, and then take the reciprocal, and you're going to get a pretty decent idea of the probability that that number is prime. But it's nice to do it a little bit more carefully with a more careful statement of the prime number theorem.